welcome to the next lecture of IC 141 Product Realization Technology. Now in today's lecture we are going to discuss what are polymers. So I told you in the beginning that all manufacturing processes are compatible with certain types or certain classes of materials, right? So in that case we first need to learn about these materials, and then based on their properties which manufacturing process will work for them, or we can design a manufacturing process for them, right? So in the previous lecture you learned about metals and also alloys. Now metals and alloys, they have high melting points, and then they are also they can be re-solidified, they can be recrystallized. So based on that we can use processes such as casting, where you melt them, give a certain shape, and then you cool them down again. But does that work with polymers, right? So first of all, what are polymers? In today's lecture I'm going to give you I will start from this very basic definition of polymers, and then you will see that based on their molecular structure, based on how they are made, based on that, how can we think of a suitable manufacturing process for them. Okay, so what is a polymer? Polymer is an organic compound. So what is organic? Organic means it is a hydrocarbon. What is a hydrocarbon? Well, it definitely contains hydrogen and carbon, because that is in the name itself. So these are carbon-based compounds, but they definitely contain hydrogen. So carbon, hydrogen, two essential elements. Other than that, they can also have oxygen, nitrogen, sulfur, halides in some cases, and so on. Okay, so now these organic compounds, not all of them are polymers. Polymers, in fact, there are also examples of inorganic polymers. There can be some inorganic polymers also, but in the case of manufacturing, we'll be dealing with mostly organic polymers. All right. The main thing that makes a polymer is the fact that they are made of monomers. What are monomers? These smaller units. So in the case of a hydrocarbon, let's say this is one example of a very simple polymer. You have a monomer, and if you join a lot of them together, so you see the blue structures on top, if you join a lot of them together, then what you get is a polymer, right? So from this picture itself, you can see that these are long structures. They are not necessarily always chain-like. Sometimes they can also be sheet-like structures, but they are definitely long structures. When they are long, that also means they contain a lot of, lot of atoms, carbon, hydrogen, or other elements that I discussed, which also makes their molecular weights quite high. So you can also call them heavy molecules. Okay, so such heavy molecules, and specifically organic heavy molecules, heavy polymers, which are made of these individual units. So some biological molecules may be very heavy in terms of molecular weight, but they may not be made of these monomer units, repeating monomer units. They are not called polymers. Polymers must be made of some repeating unit. All right, so this is the basic structure for polymer. Now, are these, or do these monomers have to be always the same? So for example, here you see that all the blue structure, if you see again on top, forget about the chemical structure, you see that the same blue structure is repeating. So let's say it's the same chemical structure, but what if I had one blue and one red structure, and then can I also make polymer from them? The answer is yes, as long as they are repeating in the same fashion, or sometimes they are chemically reacting and this blue and red is making some purple structure, and then that unit is repeating. So based on these aspects, you can also see the difference in the properties of the polymer. But the point is, they don't always have to be the same. So here I have given some example. Polyethylene, commonly known as polyethylene or polythene, that is made of same units or same monomers. On the other hand, bakelite you must have heard, is the name of a type of a class of plastic, which is phenol, a combination of phenol and formaldehyde. So if you mix phenol and formaldehyde, then some new structure is made, and maybe some byproducts like water are also produced. Now this new structure, however, is like one unit, and multiple such units can then make a polymer altogether. So they don't have to be always the same, they can be different as well. This is again the definition of organic materials that I told you. Now, when I said bakelite, you must have heard this name in the context of plastics. In fact, this is one of the first commercially available plastics. Okay, so what is a plastic? Are all polymers plastics. Because whenever we talk about manufacturing applications, especially you will see when you come to the workshop and when you make something, often people, when they make something out of polymers, they end up calling it plastic, or commercially, industrially, polymer based manufacturing is often called plastic based manufacturing, or especially plastic furniture and so on. Anything that is hard, we call it plastic. So what is plastic altogether? If you try to find a definition of plastic, you will find very confusing definitions, because some people will say, everything that is organic is plastic, or anything that is organic and used for manufacturing is plastic, or it is a class of materials which involves a lot of polymers. Here is the thing. Plasticity itself, the term plasticity itself, is used for the property of the material where it fractures and it does not come back to its original shape when a certain load is applied. That is known as plasticity. So if I take anything and I bend it, if it comes back to its shape, that means that much load, this was the elastic deformation. But if it does not come, it just breaks and does not come back to its normal position, then that is plastic deformation. So this property itself is known as plasticity, and the materials that show that property are known as plastics. In principle, there can be plastic materials that are non-polymers. So other materials can also show plasticity. In fact, at a certain load, most materials would show plasticity, right? But plastic, the term plastic, when it is used in the context of polymers, especially those polymers which are used for manufacturing purposes, in that case, still those materials that are hard and brittle, we call them plastics. It's not related to any specific chemical composition. Some polymers can be, softer, and some can have plastic. Soft, when I say soft, that means they can come back, like polythene. They can potentially come back to some extent to its original shape, but certain plastics cannot. So plastic is something that is hard and brittle, that breaks, and that does not show any elastic or very little elastic deformation, right? Okay. Plasticity, as I said, that plasticity is not just a property of a polymer. Many materials, and when in your engineering textbooks you will read that plasticity is a different story altogether. Okay, so yeah, what is it then? The difference between polymer and plastic? Polymer is the entire range of these high molecular weight molecules, or heavy weight molecules, which are made of monomer units. But plastic is sort of a subset of polymers, those materials which harden, and often they cannot be brought back to their normal shape. But again, this is also not completely true. I will come to the next slide. I'll tell you some more differences between different types of polymers. Okay, so here I have written the polymers can also be inorganic, but these are not the ones that we use for manufacturing purposes in most cases. Okay, so coming to the classification of polymers, how do you classify polymers? Interestingly, when you see that there are these very heavy molecules, now till now when we were talking about metals and alloys, we were thinking more in terms of crystal structure. We were thinking about the arrangement of atoms and not that of molecules, right? But when you have such long chain like or very weirdly shaped molecules, then you cannot have a nice crystal structure, right? Then you have to think in terms of the molecule and the forces that molecule can apply on other neighboring molecules. You cannot think now in terms of atoms. So individual atom does not have any meaning when we think about polymers. Okay, and also when we talk about defects in polymers and other properties, they are also not related to single atom anymore. Now molecule is your sort of the smallest unit that you will consider for understanding any property or anything for polymers. Okay, now how do I classify them? I can classify them as chain-like, sheet-like. That is one way of doing it also. But that is not how it's done. Often based on their applications or based on their manufacturing, based on the properties, there are many different ways in which you can classify polymers. So one very common method of classification of polymers is natural and synthetic. Why natural and synthetic? Well, because there are actually a lot of natural polymers. When we started working with polymers, rubbers and a lot of resins that come out of the trees, even wood is a polymer. Cellulose based polymers are present in various parts of the plant. We also have a lot of polymers inside our body. Biopolymers they are called. So there are basically a lot of polymeric materials that are naturally available. Do we use them for manufacturing purposes? Some of them. Not the human body polymers, but definitely the polymers coming out of the plants or trees. That we definitely use also for manufacturing purposes. Okay. Synthetic polymers are the polymers that we design. For example, polythene or different types of plastics and so on. We also have, because we are making them, we have certain control over their properties. So we can, for example, change the ratios of the the materials that make those polymers, or we can make different combinations of monomers, or we can also control the molecular weight. Sometimes it's the same chemical structure, but if you have 100 monomer units or 1000 monomer units, that will just change. The chemical structure will not change, but the molecular weight will change, and that can actually change a lot of properties. So here we have some control, and that is why we have, this is one type of classification, natural or synthetic type of polymer. What else? Polymerization mechanism. Now we will not go into the details. This is a lot of polymer chemistry. Maybe you will learn a different course about this, but there are different mechanisms that are responsible for the growth of a polymer. So when I say growth of a polymer, I'm talking right now about making the polymer itself, not making anything using that polymer, but making the polymer itself, the synthesis of the polymer itself, right? So sometimes you have two components like phenol and formaldehyde, I told you in the previous slide. Sometimes you have only one component, like in the case of polythene. So in that case, you can also have different growth mechanisms. Sometimes you have a byproduct, sometimes you don't have a byproduct. So based on these things also, there is something called step growth and chain growth, and this is one way of classifying polymers. What else? Based on the chemical structure, definitely chain-like, sheet-like. So some polymers are also, they have a cyclic structure, so that is also one way. I told you in the beginning also. One very useful classification method for us, for manufacturing especially, is when we classify polymers based on the effect of heat on them. Why is it important for us? Because when we are making something using the polymer, we are often going to heat them and cool them down. This is something, we already know it from the metals. Heat something, give it a shape, cool it down. This is something that we like to do, right? Based on the, now what will happen is some polymers, once you heat them and cool them down, they take a permanent shape. So you can do this heating cooling only once. Once it has taken a shape, then you cannot go back. You cannot melt it back, or you cannot reform it. But in some cases, you can do it. You can do it multiple times. You may have seen even with the polythene, standard polythene, you can melt it and then give it a shape again. You can melt it multiple times. So this is one very important classification of polymers, which actually divides it into two things, thermoplastic and thermosetting polymers. Only two, but I have written three here. Elastomer. Elastomer is something completely different. For manufacturing purposes, we call elastomers, we also consider this as the third class of polymers. What are elastomers? Something like rubber, something that is like almost perfectly elastic. So we were talking about plastic materials, right? In the case of elastomer, you can stretch it and then leave it, and then it will come back pretty much to its original shape, and this can work several times. Okay, so those are elastomers, and thermosetting and thermoplastic are the two primary classes of polymers that are based on the effect of heat on them. Okay, so what are thermoplastics? Thermoplastics are those polymers that can be heated and reshaped multiple times. Okay, thermosetting, of course, those once they are hardened, you cannot now bring them to their melted state again, or if you do that, they will lose their chemical properties. They will rather degrade. So you cannot again get the same material back, or you cannot shape it one more time or something like that. So that is thermosetting. And elastomer, as I said, are these rubber-like structures. By the way, rubber is one example of elastomer, and there is another example called silicone or PDMS. This is a material which, for example, you use in contact lenses. So if you've seen anybody use the transparent contact lenses, that is a material very similar. So it's a type of silicone. So this is these are also perfect elastomer materials. Some other examples also you can find. All right. Yeah, so in the previous lecture we talked about malleability and what else, the ductility of metals. So basically, can you make thin sheets and thin fibers? And in fact, it also came up in our live session that yes, we can also make thin sheets out of polymers. We can also, maybe we can also make fibers out of polymers. The answers, yes, you can, but the mechanism is not the same as that in the case of metals. So metals are crystalline materials, polymers are not. Polymers may be semi-crystalline, we'll go into that, but they're definitely not crystalline in the same way as metals, because you see that now we don't deal at the atom level, we deal at molecule level. And these are also very crazy, complicated shaped molecules, you know. So anyway, the point is mechanism, of course, is going to be different, even though you are able to make thin sheets out of it. You may not be able to call these materials malleable or ductile in the same fashion. Okay, because now everything depends upon the arrangement of chains and the forces between the chains, and they play very important roles. This can also get very complicated because your polymers sometimes behave like both liquids and solids. Okay, so the liquid part of the polymer will have some resistance to forces, which is viscosity. It's the property of most liquids. But the solid part has this entangled chain. They are rubber-like structures. They may actually stretch and get back to their standard position. So here in this diagram I have shown, this is what happens on the load if you apply certain load on polymer chains. But this is only the solid part. Remember, they will also have some liquid part. So not the entire polymer is just chains. It also often has some liquidy parts or some solvent in it. So there are also parts that behave liquid-like, but this is the solid-like part. And you see there are some entangled chain. And I pull them, they get stretched, and then when I leave the load, they go back to certain position which may be slightly different from their original configuration. So the chain, if you see in the first and third image, they are not exactly the same configuration, but the point is you can stretch and bring it back, stretch and bring it. So it has this elastic property as well as viscous property, and that is why the mechanism of pulling the fibers is going to be quite different, although you can very much pull the fibers. Okay, so coming back to thermosetting thermoplastic, actually if you try to find the differences between these two types of plastics or polymers, you will find a number of differences. You can actually do a little bit of literature search on your own. Here I have written a few things. So of course, by definition itself, thermoplastic can be reshaped after heating, which makes it multi-use polymer. And the single-use polymers are the ones that cannot be, once they take a shape, then this is like permanent. Okay, but then why do we use it? Single-use plastics or single-use polymers should always be better than the multi-use should always be better than single-use, right? Because we want to recycle the polymers and so on. But the single-use or thermosetting type of polymers, resins mainly, they are often much more stable. They are chemically stable. They are, in terms of temperature, so they are also thermally stable, and they are also hard and brittle in most cases. So when you want to make, for example, furniture, you rather want to use materials that are hard and brittle. Also, in a lot of electronic goods, for example, PCB, they are made of the PCBs are made of thermosetting resin. So a lot of uses require thermosetting materials, require a stable material and hard and brittle material, and that is why they are also used, although the use of single-use or thermosetting type of plastics is gradually reducing because of environmental restrictions. So you can go through these properties and maybe find some more for yourself, the difference between thermosetting and thermoplastic. Here in these schematics I have shown, the first one is thermoplastic, where you can see, although I have made dark blue and light blue color, basically they are all same structures, and you see that you have these chains basically floating around. They are floating around, but they are not forming any chemical bond with each other. Okay, so they're floating. It's like you can freeze them, and then again when you heat, they start to float again, they start to go far from each other again, very similar to what happens in the case of any melting. But in the case of thermosetting plastics, what you have is these, with the red dots I have shown that there are links, chemical bonds between these chains, and now once it has taken this solid shape, it cannot just move without being chemically destroyed. So it will degrade, or if you keep on heating it in air, it might burn, but it will not melt again. It cannot be reshaped. So that is how these different types of polymers look like. Now when you have these sort of sideways interaction or bonding between two chains, if I take chain number 1 and chain number 2, they are maybe floating, but they are not bonding with each other. That is the case with thermoplastic. But if they are bonding sideways, okay, and forming a reasonably strong chemical bond, that is called, that type of bonding is called cross-linking, and then these material become thermosetting. So cross-linking is also a very important term when you understand anything related to polymers. What are the other important terminologies? Well, there is something called curing the polymer. This is also something you'll hear a lot if you melt the polymer and you want to solidify it again, whether it is thermoplastic or thermosetting. What you need to do is you need to provide certain conditions. For example, even if you want to provide certain heat, for every polymer there may be different temperature at which it solidifies, right? It's like other metals, other materials as well, right? So each polymer has its own set of conditions that need to be provided, whether it is heating, whether it is cooling down, whether it is sometimes exposing to a certain radiation and things like that. Whatever is that condition, if you provide that condition and then allow it to cross-link, then that process is known as curing the polymer. Okay, what is the other? One more important definition that you need to learn is something called glass transition temperature. When we talk about polymers, we don't talk in terms of melting point, but rather glass transition temperature. So what is glass transition temperature? The name itself has something to do with glass, it's something to do with transition, right? So it is a transition of the material in terms of its physical properties, from glass-like properties to rubbery and then liquidy properties. And that temperature below which the material behaves like a glass is known as the glass transition temperature. All right.